Good morning, dear students. In this section, we will learn about steroids. Then, what are these steroids that we need to understand first? They are a group of natural or synthetic organic compounds. Then, how we can understand this compound from other different compounds? We can characterize it by its unique molecular structure of 17 carbon atoms. We can see that in this picture. So, it has such a configuration, such a molecular structure of 17 carbon atoms. As we look to this structure, we can understand that they present three cyclohexane ring. Three cyclohexane rings and one cyclopentane ring. Then where is that cyclopentane ring? This one. So these three cyclohexane and this one cyclopentane ring, it forms the nucleus of the steroid, and to this are coming and attaching different groups to form different types of steroids. I hope that what are steroids is very clear to you. Then let's see some examples. Okay, so examples include all the sex hormones that our body producing, then adrenal cortical hormones, bile acids, then sterols of vertebrates, molting hormones of insects, and many other physiologically active substances of animals and plants. They are all steroids. And also, all these steroids are natural one. Then where we can see the synthetic one in the form of some medicine or oral contraceptives. In all those forms, we can see the synthetic steroids. Then how different types of steroids are forming, how it become differ. That is based on the nature of the attached group. At the end, let's move back to the former slide. So here we can see the special group. So based on the type of the group, nature of the group, and also the configuration. Configuration means with respect to each bond, what is the spatial arrangement of atom. So based on the configuration, based on the position of the attachment of the group, based on the nature of this group, we can form or steroids differ from one another. Okay.
Next, we are going to see biologically important steroids, and among them, cholesterol is the important steroid. As we heard about that term, the another critical issue that comes to our mind is heart attack. So, cholesterol and heart attack have some relation. It's very important to keep a normal cholesterol level in our body to prevent heart attack. So all those things we will learn in the coming part of this video. Anyhow, first we need to understand about this cholesterol. The word cholesterol, it is derived from some Greek words. Which are those Greek words? Those Greek words are call, then steros, and all. From these three words, that cholesterol, that word emerge. Call means bile, steros means solid, and all means alcohol. And then need to understand about its distribution, where all in which all regions normally the cholesterol level can be high and where all its level can be low. All those things also we need to understand. uh, Almost all nucleated cells can synthesize cholesterol. Understand? Almost all nucleated. which all cells have nucleus, all those cells can synthesize cholesterol. And about its distribution, for understanding this distribution, we are considering a healthy man of having 70 kg. So 70 kg is a standard healthy weight of a normal man. In his body, the healthy level is 140 gram of cholesterol. Don't be afraid on looking to this figure. It can vary. Anyway, this normal value can be for a healthy man is 140 gram. And where all this 140 gram is distributed, the major site of having this cholesterol, they are three sites are there. That size we can memorize by this short form BMA. B for brain, M for muscle, A for adipose tissue. And all these area, they contain cholesterol in maximum amount. Maximum amount means amount that is normal. Normally can have for the 70 kg man. It is 30 gram. Commonly, a 30 gram is possible. It is healthy to have in those areas from where all in brain, muscle, and adipose tissue. 30 gram is healthy to have. And compared to that, a little bit less is good to be present in skin, that is 20 gram, and in blood 10 gram is healthier, and in liver and spleen 10 gram is healthier, and 5 gram only in bone marrow, 3 gram in alimentary tract, and only 2 gram in our adrenal glands. So that's just for an information possible, but these three sites we need to memorize. Brain, muscles, and adipose tissue, they are the regions where cholesterols present, cholesterol maximally present. These are the areas: brain, muscles, and adipose tissue. Then regarding its chemical property, it is light yellow. Its color is light yellow, crystalline, solid, and appearance, it's a notch. Notch means is an intonation V shaped like intonation. This is the means structure appearance of this cholesterol, notched appearance. As we observe, means examine the cholesterol to the microscope, we can see a notched appearance. It is a light yellow, crystalline, solid. And this cholesterol is soluble in which all things? It can be soluble in chloroform. Chloroform, it is soluble. Chloroform, we are all familiar. Okay, anyway, and also it is all dissolving in all fat solvents. Fat solvents. It is lipophilic. So cholesterol is soluble in chloroform and fat solvents. And it is the important animal steroid. So which is the important animal steroid? Animal steroid is cholesterol, and all the other steroid compounds, they are forming from this cholesterol. So we can say that it is the foundation base from which other steroid compounds are forming. And whereall, regarding the occurrence, it is widely distributed in animal tissues. I already told you that important animal steroid is this cholesterol. So it is widely distributed in animal tissues, but it is absent in prokaryotes. Prokaryotes totally lacking this cholesterol. And in plants also, this cholesterol is absent. Where all it is absent? Prokaryotes and in plants, the cholesterol is absent. But in plants, some other plant sterols are present. That doesn't mean that plants totally lack of all steroids. It is deficit of this cholesterol only. If we take the case of bacteria and plants, steroids similar to this cholesterol exists. What is its name? Steroids similar to cholesterol is present in bacteria and plants. What is its name? Its name is hopanoids. Hopanoids. Hope. Anoids. And then we need to by her the names of some scientists relating with the cholesterol who isolated this cholesterol for the first time. Name is typical Pollitier de la Salle. Pollitier de la Salle in 1758. From where he isolate this cholesterol? Gallstones. Gallstones means they are some crystalline structures composed of this cholesterol and bile, and it is forming inside our gallbladder. If that stones are forming there, it is a it's an unhealthy condition, need to be treated. Otherwise, it become complicated. So anyhow, in that gallstones, these cholesterols are first isolated by the scientists, and who explain its characters. Cheval Me characterized cholesterol in 1818, and its complete structure. Its structure is very interesting, and its structure of cholesterol is enunciated by Heinrich Wieland. Heinrich Wieland, that name we cannot avoid, need to memorize anyhow. We Heinrich Wieland in 1980. For that contribution, he got Nobel Prize also in 1927. Next, we are going to see the structure of cholesterol. What about the structure of cholesterol? In the beginning of the section itself, I clearly explained to you what is the pattern, what is the appearance of the steroid. And it is composed of 3 cyclohexane and 1 cyclopentane that forms the nucleus. And to that nucleus depends upon what type of side groups or side chain is attaching, that determines the type of the steroid. As this group come and attach with the nucleus, the core part, it forms the cholesterol. And let's have a look to its components in a GIF. It is a fused ring system of 3 cyclohexane ring and 1 cyclopentane. These 3 rings are designated or labeled or named as A, B, and C, and the cyclopentane as D. And these arrangement, the special pattern of the attachment of these 3 cyclohexane that have a name, it's called phenanthrene arrangement. That arrangement is known as phenanthrene arrangement. Okay. Then totally how many carbons are present in the structure of cholesterol? 27 carbon atoms are present. Up to here 17 are there. Then 1, 17, 18, 19, 20, 20, 21, 22, 23, 24, 25, 26, and 7. 27 carbon atoms are present in the structure of cholesterol. And also we can see one hydroxyl group at the third position, and this hydroxyl group is a characteristic property of all sterols. And also this OH group, it is beta oriented. Beta oriented means what? That bond is orienting above the plane of the ring. As it is above the plane, it is represented by a solid line. Then you might have think that if it is an alpha oriented, then in what form we can represent? Then that time we can represent that bond in dotted line only. If it is a alpha oriented means it project or it drops down the plane of the ring. As it is, as here this OH group, it is projecting above the plane of the ring. That is why we denote that bond with a solar line. So that's about the structure. And also we can see one double bond here. Okay, between fifth carbon and sixth carbon. It has some relevance. I will tell you in the coming section, in the below part itself. And the eighth carbon, sorry, and eighth carbon, this one is eight carbon beta oriented side chain that forms the sterol to a cholesterol. So that 8 carbon, this much portion, 8 carbon, it is beta. That's why it is represented by a solid line. Beta oriented side chain is attaching with the 17th carbon. So by that way, it becomes cholesterol. Okay. Then we are going to see about the isomerism. What is isomerism? We have already learned about isomerism in detail in carbohydrate chapter. Anyhow, I am just brushing up your memory. Isomerism means many different types will be there. All have same structural and molecular formula, but the spatial arrangement of atoms will be different. That gives isomers. Okay. Anyway, as in the structure of this cholesterol, there present so many centers of asymmetry. It is possible to have so many different types of isomers, and it is difficult to talk about all the isomers here in this context. So that's why I'm mentioning about only two isomers that is forming because of some change, one change that happened to this bond. If this bond is reduce, then it will convert to a single bond and one OH group will come here. And it will result in the formation of two isomers. One is called cholestanol. Cholestanol, its structure is given here by breaking that bond, by reducing that double bond here. And look, here one H is forming. And what about its orientation? It is alpha oriented. I already mentioned to you that if the orientation of a bond is alpha, that is, if it is projecting below the plane of the ring, it is representing with the dotted line. So that is why we can see dotted line here. Okay. So that is cholestanol. The another isomeric form is called coprostanol. Here, look here. Here that hydrogen bond, it is orienting above the plane of the ring. That is why it is denoted with a solid line. So that's about here itself. We can understood that the orientation of that bond is different. So that give rise to two isomers. And where these isomers are forming in our body, this cholestanol and coprostanol, these two isomers are forming as the cholesterol get digested in the intestine. How? With the help of some bacteria. With the help of some bacteria. So, with the help of some bacteria, as the cholesterol get reduced in our intestine, these two isomers are forming. Okay. Next, we are going to see about the absorption. How cholesterol that contained in our diet is absorbing, how it is getting to different parts of our body. That's why that I'm going to explain next. So we are taking diet. It is coming to our stomach, and we know that on the side pancreas. It's not that much visible. Somewhere here, pancreas is present. And from the pancreas, an important enzyme, cholesterol esterase. Esterase. Cholesterol esterase. It is breaking the cholesterol ester. Cholesterol plus fatty acid is coming in that form to the stomach. Cholesterol plus fatty acid that give a cholesterol ester. So that cholesterol ester need to break up, need to break down. It is broken down by the enzyme cholesterol esterase. Cholesterol esterase. This enzyme. Okay. And by that way, what will form? Cholesterol plus fatty acid. What will form as the end product? Cholesterol plus fatty acid will form there. I will show you. So this is cholesterol ester. This much is cholesterol. This is the fatty acid. And as it undergoes hydrolysis with the help of the enzyme cholesterol esterase, what is forming cholesterol and fatty acid. Okay, next, then the free cholesterol available because of that reaction, it is packed packing up inside the micelle. Just like as we bought something from shop, we are packing with some paper wrap or anything like that. Like that way, that free cholesterol, it is wrapped in some micelle. I think you all are familiar with the micelle because of the special arrangement of fatty as some droplets are forming, and inside this, that free cholesterol packing up, and it's called a micelle. And in that form, it reaches the intestine, small intestine. In small intestine, I'm just drawing in a magnified way. Only then we can understand. And in small present mucosal cells are there. Okay, and now this micelle have reached here. Micelle. This is micelle, and it is taken inside the mucosal cell with the help of some special enzymes. So, only those cholesterol that is in the form of micelle can be absorbed inside the mucosal cell. Okay, a specific protein is required for the transport of cholesterol into the mucosal cell from the intestine. And inside the mucosal cell, I'm again redrawing in a big size that mucosal cell. And now that cholesterol in the form of micelle is inside the mucosal cell. It is again re-esterified. Again, it is forming to an ester, re-esterified. And again, it is packed in some other micelle called chylomicrons. Because here, anyhow, the cholesterol reached inside the mucosal cell. Then, to prevent it from again combining with each other, some rolls, balls are forming using this small or discrete cholesterol units, and that small balls are called chylomicrons. It is just similar to the way that we are using we are making balls using dough. Okay, just for making you understand, that's why I'm giving that real life example. Anyhow, that cholesterol units, to prevent it from combining with each other, it is packed in small ball like structures called chylomicrons. I will show you the structure. Chylomicrons. So these are that chylomicrons, small ball like structure. And how that small ball like structures are forming? It is composed of cholesterol, we can see. In this way, cholesterol is packed inside that chylomicron. Along with that, triglycerides are there. Triglycerides are there. Then phospholipids are here. And then proteins are here. All these form a ball like structure, and in that form, this chylomicrons, that villi are present in the intestine here. Again, I'm going to draw the villi in an expanded way, and in the core of the villi, lacteal is present. Lacteal, and that chylomicrons reach the lacteal, and through the lacteal, finally it ends up in blood vessels, and and then it finally again reach the liver. Okay, so in that way its absorption happens. Okay, then there should be some method to regulate the absorption limit of the cholesterol. Otherwise, the cholesterol level in our body will steepens. So, which are those methods that also we need to understand? There is one protein. Its name is NPC1L1. NPC1L1. So what is its role? This is a protein that is helping in the absorption of cholesterol. And if there is some medicine to interrupt the action of this enzyme, then we can regulate the absorption of cholesterol. So an example for such type of drug is ezetimibe. It will interfere the action of this protein and will reduce the absorption of cholesterol. That is one method. And also there are some complexes, protein complexes. Which are those complex? One among is ABC. ABC is ATP binding cassette protein. It is a transporter protein. Along with that protein, I'm just drawing ABC, and along with that, two other proteins are also joining. They are ABCG5 and ABCG8 in the form of a dimer. They are joining with ABC, and what they are doing in the intestine itself, its regulatory activity works. How it regulates in the intestine? We have just learned that the bile packed cholesterol that reaching the intestinal lumen is taking inside the mucosal cell for further absorption. As this step happens here, this complex bring about the secretion of an amount of cholesterol back again to the lumen, and by that way it prevents the excess loading of the cholesterol inside the chylomicrons towards the liver. So by that way, the absorption level or the amount of cholesterol that is absorbing to the body can be regulated. Clear? So immediately after it is absorbed to the mucosal cell, at the moment itself, because of the influence action of these protein complex, a portion is secreting again back into the lumen and will be eliminated from our body. So by that way also our body can regulate the absorption level of cholesterol. Okay. So by here I am going to wind up today's section. In the next video we will learn about the biosynthesis of cholesterol in detail. Thank you.
I'm an icon, man. And my girl about a 10. I should fuck her in the Benz.